So folks, in the previous video I showed you the various tests for convergence that we use when working with series in general. And so I want you to practice those tests for convergence in this example here. So I'll do the first one with you, and then I'll leave you to do the second, and then we'll keep going. So in this case, hopefully you've learned that the function e to the x, I know this is e to the n, but the function e to the x increases very rapidly, and the function x increases less rapidly. And so this ratio is going to increase as the value of x, or n, increases. I think it's important to realize that eventually we're just going to be adding on bigger and bigger terms to this series. So asking the question, what is the sum of this infinite series, well, it doesn't converge to any sum at all. But the quickest way to show this, I think, is with that test for divergence. If you look at the limit as n approaches infinity of this sequence, e sub n, or e to the n over n, and what we're going to do is we're going to say it has the same limit as x approaches infinity of the function e to the x all over x. Because if I were to plug in a whole number, because remember, n only takes on counting numbers, generally is how we think of it, or integers depending on the indexing. But here, I guess we'll have, oops, folks, this should be a 1 here. So the first value for n is 1, the next value for n is 2. But notice that these are going to agree with each other at all values in, all counting numbers. But if I think of it as a function of real variables, then I can bring real variable calculus into play. So I don't really want to go into any further than that, why I'm able to connect the limit of this sequence with the limit of this ratio of two functions. If you have any questions on that, though, I'd be happy to go through it. So this we learned in first semester calculus is best evaluated maybe using Hopital's rule. So we've got the limit as x approaches infinity of the derivative of the numerator all over the derivative of the denominator. And in this case, this approaches infinity. So this series diverges by the test for divergence. So what I'd like you to do is I'd like you to try number 2 here on your own, and I will have a hyperlinked solution to this. So give that a shot and see what you come up with. And I'd like to jump down now to number 3. So please do number 2 before you move on to number 3. But here we go. In this case, I've got a factorial, and I just want to remind you that the expression n factorial in general means to take n times n minus 1 times n minus 2 to 3 to 2 to 1. So it's to multiply all natural numbers starting at n down until we get to 1 to one another. So for example, if I gave 3 factorial, that's the same as 3 times 2 times 1, which would be 6 in this case. And let's just add to it the caveat that we choose to define 0 factorial to be 1. That's what enables me to start this particular series here at 0. So if you look back at my notes, and hopefully the mouse will cooperate, the first thing we should do is, if we can, try to apply the test for divergence. And I don't think it's entirely clear until you've done some work with factorials, but essentially factorials eventually take over. And so this limit does go to 0. The limit of these terms goes to 0, but we can't, that doesn't tell us anything other than we just need to continue working because we haven't ruled anything out at this point. The series, I don't believe, alternates. No, it does not. And we can't use the root test because we don't have them all to the same power. So I would recommend, at this point, the series has factorials and terms raised to the nth power or something like that. Let's try the ratio test on this. So let's go ahead and do so. The ratio test says what we're going to do is we're going to look at the limit as k goes to infinity of the ratio of the next term over the current term. So we will take a sub k plus 1 all over a sub k. We do that in absolute value, and we look to see whether or not this converges to a number smaller than 1 or not. So if this limit comes out to be 1, in fact, let's scroll up and see that. here we have our alternating series test, or ratio test, excuse me, here. And if the limit comes out to be a number, or if it comes out to be infinity, we can make some statements. So if the limit comes out to be a number smaller than 1, then we can conclude that the series converges. If the limit comes out to be something greater than 1 or is divergent, then the series diverges. And if the limit is 1, then the test is inconclusive. So what I'm doing here is I'm taking the ratio of the next term over the current term, and we want that amount to converge to something less than 1 if we are hoping for convergence for this series. So let's go ahead and do so. This is the limit as k approaches infinity of, so writing out the k plus 1 term, that would be 6 to the k plus 1 divided by k plus 1 factorial, all divided by 6 to the k divided by k factorial. And what I can do is we've got division by a fraction. Usually with these it's a lot easier if you do that trick of inverting and multiplying. So I'll write this as 6 to the k plus 1 all over k plus 1 factorial and multiply that by k factorial all over 6 to the k. So then this is equal to the limit as n approaches infinity. And now I can do some canceling. I'm going to do this slowly because it might have been a while since you've seen it. So remember, of course, I could write 6 to the k plus 1 as 6 times 6 to the k. I'm going to leave that k factorial as is. And in the denominator, I'm going to rewrite k plus 1 factorial. Remember, what is factorial? It means to take this number right here and multiply it by 1 smaller than it, and 1 smaller than it, and 1 smaller than it. And so I can write this as k plus 1 times k factorial, and because I really have k times k minus 1 all the way down, but I'll just leave these factors sort of folded up as k factorial. And so now we've got some terms that cancel. The factors of k factorial cancel, the factors of 6 to the k cancel, and so we're left with the limit as n approaches infinity of 6 over k plus 1. This limit's almost as good as we could hope for, in that this limit is 0. And so the series converges by the ratio test. Okay. I'd like you to, and I've got a solution hyperlinked for you, I'd like you to go ahead and do number 4 on your own and then look at the solution. But I want you to use the ratio test on this because I want you to practice using it. So you could, if you know some other tricks, you could use the test for divergence on this. But I'd rather you use the ratio test to make sure you get some practice with it. So work through that and then take a look at the key, and then I'll join you in the next one. So I don't have a lot to say about this one, but if you run through my list of my checklist that I've got here, we could do the test for divergence. It would fail the test for divergence, which doesn't tell us anything. It could still diverge or it might converge. We don't know. But the next one is to check the alternating series test. And if I go look at my alternating series test up above here, what we need is a series that alternates, meaning we've got it's going to change sign depending upon the value of n, alternate between them. And we need the part that's non-alternating. We need it to be decreasing and convergent to 0, and what else? There it is, always positive. So what I could do here is I could think about this series as a series from j equals 0 to infinity. Oops, I did it again, folks. Oh, shoot, I think that's a song. Let me change this to a 1 because I can't have a 0 there. 1, and we have negative 1 to the n, and then I'll write it times 1 over n squared. So this part right here is playing the role of what I call b sub n in my description of the alternating series test. So notice 1, the series alternates, and 2, b sub n is 3 things. B sub n is greater than 0 for all n. B sub n is decreasing for all n, or at least for some n value, for some counting number onwards. And finally, b sub n converges to 0 as n goes to infinity, meaning these terms get smaller and smaller. So all of this taken together, 1 and 2, tell us by the alternating series test that this series converges. And that's all I've got on convergence. So in the next video, we will do a review of power series, and we'll actually find the radius of convergence for a few power series.